Hello and welcome to this Oasys webinar on GSA 8.7. What is coming up in the new version GSA? Chris.
Thanks, Peter. So yes, I'm one of the GSA developers. You'll be hearing from others too. Steve, Thomas, and Jerome Session will all be presenting different parts of this presentation. So I'm going to start by talking about, there we are, talking about the handling of large models. Well, the improvements that we've made in GSA 8.7 in the handling of large models. So I'm going to be selecting some of the items from this list. Probably the most significant item is the handling of lists has been optimized. Not immediately obvious how that might help, but if you've got a huge model with many thousands of element lists and you're wanting to display element forces and moments, then those lists need to be parsed in order to establish what loads are applied to each element. We've optimized that such that, well, in the particular case that we were reviewing in implementing that feature, the display of bending moments reduced from in excess of 10 minutes down to just a few seconds. So it was a very significant improvement in that particular case. Of course, it depends on the model being looked at. Moving down the list, grid load expansion is faster, often 10 times larger than faster than in previous grid load expansion methods. Steve will be covering that a bit later in more detail. Response spectrum analysis is faster, again, 10 times faster or thereabouts. So, quite significant improvements there. We've introduced a new concept in GSA, that of an assembly. So, what is an assembly? An assembly is a collection of elements. It's well, an example of an assembly, or an example of the use of an assembly, is a core in a tall building. So the idea of the assembly is that you can treat that assembly as if it were a single element, so get results out for that collection of elements, and we'll see how that happens. So the assembly is defined in terms of a list of elements. There's an axis associated with it, which defines the local axes of the collection of elements. And well, you can see there are various other things you specify to define the assembly. And having specified an assembly, and if you've analyzed your model, then you can produce results for that assembly, for that collection of elements along the x-axis of the assembly. So here we're seeing some charts produced for moments in the YY and MZZ moments for this assembly. But also you can produce display results in the output views and graphic views in the way that we're familiar with. So here we're seeing contouring of an assembly and diagrams of an assembly, and also output views. So, as an indication of how we've integrated assemblies into GSA, you can refer to an assembly in an element list, just as you can refer to a grid plane in an assembly in an element list. And when defining what elements are to be displayed in a graphic view, you can refer to an assembly, just as you can refer to grid planes and element lists. And furthermore, there are some labeling options for the assemblies. Moving on to the new mesh generation engine. So we've slotted in a new mesh generation engine, which is referred to as mesh tools within GSA. That is consistently faster at producing meshes than the previous quad build mesh generation engine, producing a smaller mesh and a better conditioned mesh. There's no change to the approach of specifying how the mesher should generate the mesh, not in its general approach anyway, so you're still specifying a region which isn't defined in terms of areas, lines and nodes, etc. But the detail of some of those mesh attributes has changed. And also, and significantly, there's an option to include try elements into your mesh. So more generally, we've implemented an option in terms of mesh generation. We've implemented an option to specify the element size for the region, which covers all aspects of the region, unless overridden by the element size specified for the line, which again dominates unless there's an element size specified at a node. The old mesh generation engine remains available. We don't know of any circumstance where that is preferable to the new one, but you never know. And there are tools for converting the mesh attributes from old to new and vice versa. So here's how the region definition looked in the old quad build, for the old quad build mesh generator. So you'll see that the option to allow try elements to be generated is disabled here. And if you press the advanced button, you see that these options are offered, familiar to those of you who've used the old mesh generator. If you go to the mesh tools representation of the region definition, then yes, we can select to include try elements. And if we click the advanced button, then, well, here's an interesting one. You can specify the maximum and minimum internal angles for your generated elements. And that's how the try elements are introduced to the mesh. If the resulting element is outside the limits defined by those max and min angles, then try elements are introduced to improve the condition of the mesh. So here's a mesh generated using quad build, and I can tell you that there were well, just under 1,500 elements in that mesh, and the highlighted elements, the selected elements, those 5, are poorly conditioned. They would result in warning or a severe warning in the analysis. Whereas the mesh tools generated version of the same of mesh generated for the same region is something under 500 elements, so that's a third as many elements, and all of them are in good condition. And you can see that some of the elements are try elements in this sort of area of the mesh. So those have been introduced to improve the condition of the mesh. Curved and explicit members. Sometimes it's useful to define curved members. We can define those in the same way as we can define curved lines. So either by a third point on the arc or by defining the radius. Whereas explicit members allow for a much more generally shaped member. So you define your end topologies plus a number of internal nodes. And now I'm going to pass you over to Steve, who's going to talk about, initially, grid load expansion.
Thank you, Chris. So first of all, the grid load expansion. As Chris mentioned earlier, this has now been speeded up, and that's been done by introducing some new algorithms for handling that. But before we look at those, there are some revisions have been applied to the grid planes themselves. So in the past, there was some confusion as to what the difference was between a multi-way and a two-way spanning grid plane. To avoid that confusion, we've merged the two of them into a single option, and then you select which particular algorithm you want to use in order to distribute your loads. So legacy is the existing one, and we've introduced 3 new ones which are really one method with variations on that. So we call that plane approximation. That is a different approach. It doesn't require as many calculations. So as a result, it's a much faster option. But as before, we want to make sure that we maintain equilibrium with the applied load. So just taking a very simple example, if we have a rectangular panel like this, the legacy one gives that slightly odd-looking jagged result. The plane approximation, as you can see, makes it a lot smoother, but we get a bit of load sort of concentrated mid-span along the edges. The plane approximation with the smoothing takes out that emphasis at the center of the span and smooths it along the whole of the edge. But the one which we think is probably the most useful is the plane approximation with the corner effects taken into account. And that gives you the distribution like the back of an envelope, which you would normally be looking for when you have this kind of loading. So that's grid load expansion. Various changes in modal and seismic analysis. So looking first of all at modal and Ritz analysis, the eigensolver has been improved, so there's better reorthogonalization, which gives us better and faster convergence. But we've also introduced the option to apply a shift. This means that if we want to get eigenvalues, which would either be frequencies or load factors, in a particular range or around a particular value, we can do a shift so that we recover those particular ones in preference to the others. On the Ritz analysis, one of the things we found is that symmetric structures might not pick up torsional modes, which do exist in reality. So we've added an option to randomize the Ritz load vectors. This means that we put a little bit of non-uniformity into the loading. So even if it's a symmetric structure, there's a little bit of non-uniformity which will excite the torsional modes. So this will give us slightly different results from running a standard Ritz analysis, because we're obviously picking up different modes, but the modes which we do have which are similar may have slightly different frequencies. There shouldn't be anything significantly different, but it's just a feature of the way that Ritz analysis works. For doing a dynamic analysis, we can assign different masses in different directions with the lumped mass element, something which is occasionally useful, but most of the time you'll be able to ignore that. And the dynamic details which we provide have been updated a little bit, in particular giving more information about inertias, just to make it easier to see if things like torsional effects are significant. On seismic analysis, the response spectrum analysis is now faster, as Chris mentioned. That's particularly the case for large models when you've got a large number of modes that need to be combined. The response spectrum tasks themselves have been extended, and so now the basic responses are defined directly in the task. So that particular module, which was under the dynamic specification, has now gone. And you specify those directly. Likewise, the story drifts are now included directly in the task. They're not something which are calculated during the analysis. They're a post-processing option, really. And so while they're in the task, they can be modified post-analysis. You don't need to have decided up front exactly where you want to calculate story drifts. Stories themselves have changed, so they no longer exist as a separate entity. They've been merged with grid planes and they become a special type of grid plane. And along with that change, we also have story views, which allow you to get a plan of a particular story, and it includes the column outlines. So it's just a different way of looking at your model. On the accidental torsion, we've modified that so it now covers all the seismic codes that can be used in the response spectrum analysis, and there are more options to specify the base shear. All right, patterned load. This is a new feature, and it's based on a paper which Don Ho in Hong Kong has written. And he's looking at how we cope with the problem of patterned loads as specified in the various design codes. How can we make sure we've covered all those particular cases? So Don has come up with a methodology. What we've done is to add some tools just to make this something which you can use in GSA. And in particular, we've got 3 tools. The first is to create load panels on a story. So we simply take a floor level, create load panels. Then the second tool allows us to set up a set of loads on these panels which we've generated. And the third one allows us to do the final combinations to make sure that we've covered all the possibilities we're interested in. So these sit in the Tools menu under Building Analysis. So we can create the load panels on the stories. It's fairly straightforward. Create patterned load. So what we do here is we decide which are our dead and imposed loads. We specify adverse and beneficial factors for those, and then this will go off and generate a whole set of load cases for us, which will look at the loads we need to cover all possibilities. And the final one is the one to create the patterned loads. So we're now picking up the analysis cases which we've looked at in a static analysis for mean loads and difference loads. If that doesn't make sense, if you have a look at Don's paper, that becomes much clearer. We can also add in other load cases if we need to as well. So the basic workflow is to build your GSA model just as you normally would. Use story grid planes to define the floor levels. You can then create the load panels on those. You define your dead and imposed loading and any other loading just as you normally would, but you can then use the Create Patterned Loads tool to set up all these different adverse beneficial factors in the separate load cases. Once you've done that, it's a normal linear static analysis, and then using the pattern load combination generator to set up the various combinations to make sure you can envelope all the results. Right, analysis with creep, and this is a very simple approach to analyzing with creep. Essentially what we're doing is we know that concrete elements can experience creep, and in the past we've had long-term and short-term concrete. This was a sort of rough and ready way of doing it. What we're doing is we're removing the long-term concrete option and replacing it with the option to specify a creep factor in the staged analysis. So you specify the phi factor for creep, and then if you're analyzing that stage, any concrete materials will get the E and the G values modified to represent the effect of creep. So the effect of this is that you can set up your model, and it's much easier to compare long and short-term analysis within a single structure. And at that point, I'm going to hand over to Thomas.
Thank you, Stu. Okay, I'm going to briefly introduce the following new features in GSA 8.7. So the first of all is a new design code. So because GSA used by many people from many regions, so a different design code is required. So in this version, we have added 2 new steel design code that's listed on here. So it's a European steel design code for Singapore standard, and another one is a South African national standard. So you know GSA can also do RC slab design. So we have added this new concrete design code for RC slab design. So American Concrete Institute design code, and Hong Kong, Indian, and Canadian. So 5 new codes being added. Of course, 2 of them are American code. One is imperial unit, one is metric unit. For footfall analysis is partly rely on a design standard or design code. So just for your information, I may say a little bit more about footfall analysis on new design code. So footfall analysis, the three main procedures. So firstly, we need to know the mathematical representation for footfall loading. Once we know the mathematical representation of the footfall loads, we can do dynamic analysis to get the dynamic response. Then we need to evaluate the dynamic response to see whether it meets the certain requirements. So in this version of GSA, only the evaluation of footfall response has been updated. It's using a new code. Other bits has not been changed. So the update you can see on the slides, the evaluation of footfall response. That means the calculation of response factor is based on the following two codes. Actually, they are related. You can say it's one code. In addition to this, we have added user-defined criteria. So before, it wasn't available. So now, if you have your own criteria to evaluate footfall response, you can define your own criteria. We call it frequency weighting curves. Then GSA will evaluate the response based on the criteria you defined. So that's an additional feature. You see the nodes. Before, only one standard available. Now we add more. Just for your information, so we are not only update the using the new design code to evaluate footfall response. Actually, the calculation of response factor, I mean the measure to calculate response factor, has been changed a little bit. So before, the response factor is calculated using acceleration response divided by baseline acceleration. Baseline acceleration is taken from the standard. So now the way to calculate response factor is different. You can see the response factor is calculated now using frequency weighted acceleration divided by 0.05 meter per square second. So that's a new way to calculate response factor. Because of this, we are not using baseline acceleration anymore. We are using a frequency weighting curve. From the frequency weighting curve, we can get frequency weighting factor. Using this weighting factor times the frequency times the acceleration we analyzed to get the frequency weighted acceleration, then we get a response factor. That's a way to do it now. There are three frequency weighting curve have been embedded into GSA now. So you can choose which one you want to use. You can see it's listed on here. So they have different use for vertical vibration, and you want to evaluate health, comfort, or perception, or some other criteria. You may choose different curves. Basically, WB is the default curve you normally use. Here are the three frequency weighting curve are plotted in logarithmic scale. You can see the curve, they are quite different. Just for your information, I said in previous version of GSA, we only use one standard to evaluate the footfall response. So that one is equivalent to WG. So now we have more than one. So the next new feature is the shell element in nonlinear analysis. You know, GSA can do nonlinear analysis using beam element, bar element, etc. But shell element is not available before for nonlinear analysis. So in this version, we have implemented code for try 3 elements for nonlinear analysis. If you have used GSA shell element, you will know there are two different formulation for shell element. One is bilinear, one is Ullmann-Cook. So the shell element for nonlinear analysis is using Ullmann-Cook. It's no option for you to choose. You know, when you do linear analysis, you can choose Ullmann-Cook formulation, bilinear formulation. for nonlinear analysis, is Ullman-Cook, always Ullman-Cook measure. A shell element can be used in nonlinear analysis, but we need to bear in mind that the formulation is still using small strain assumption. So that means the deformation can be large, but the strain should still be small to guarantee the results are accurate. But normally, if you do a shell element structure analysis, the strain will be small if you are using concrete steel material, unless you are using rubber material. That's not the case. The next new feature is wall element enhancement. I said enhancement, you probably guess. Wall element was already in GSA, in previous version of GSA, but with some limitations on use. So in this version, we have removed some of the limitations and enable some of the analysis. You can see on the list. Before, a wall element has to be rectangular. So no other shape was available before this version of GSA. So now this limitation has been removed. Before, wall element can only use local axis. So the local axis will define the x direction of the wall element. That will be from node 1 to node 2. Now you can define using any axis to define the wall element. The benefit is, you know, when we're using wall element, we normally want to know the primary direction, secondary direction. So the primary direction is the local x direction, and the secondary direction is the local y direction. Before, if you want the primary direction vertical, you have to manipulate the topology of the wall element to make sure all the wall element primary direction vertical. Now you don't need to do that. You just define your 2D element in any way. Then you using axis, you define the axis x direction is in vertical direction. So in this case, you can plot the moment forces in primary direction without too much effort. So another feature for the wall element is wall element you can do buckling analysis using wall element model now, and you can do P-delta analysis as well. Before, they were not available. But as I mentioned here, you will need to bear in mind that if you do buckling analysis or P-delta analysis, the buckling will not occur within an element, and the P-delta analysis effect is ignored within a wall element. Wall element is a large size element, can be a single story high. So within the single story, the wall element will not buckle. So here is one example for example, a building core modeled by shell elements and wall elements. They are buckled globally. You can see the results are almost the same. Difference probably about 1–2% difference. Here is the same model in higher modes. For the shell element model, you can see local buckling occurred, but for wall element model, there's no local buckling. So if local buckling is a problem for your core you modeled, you probably need to use shell element rather than wall element. But normally for a high-rise building, local buckling is not in control. The next feature is faster RC slab design. We normally say RC slab design in GSA, but I need to mention that it's not only RC slab design, it can be RC wall design, because we say RC slab. The slab direction could be vertical, horizontal, diagonal, any direction. So RC slab design is an iterative process. So the reason is for achieving accurate results. Because it is iterative, it is a bit time consuming. I think if you have a large model, you want to get reinforcement area, you may need to wait for a while. But for small size, medium size model, I think it was okay. It's pretty fast. Only for large model, it may be a little bit slow. But nevertheless, so we have speeded this up in this version. Give you an option, you can use a faster measure to do the RC slab design if you have a large size model. So when the faster method is going to be used, if the following three conditions are met. So firstly, you need to enable faster method. So if you want to use faster method, you need to define it, enable it in Oasys Slab design property definition. You go to Oasys Slab property definition table. When you double click it, open a wizard. On the wizard, there is an option you can enable faster design. The second condition is the loading for the slab, either primarily in-plane bend loading or primarily auto-plane bending. If both in-plane force auto-bending are roughly even, fast method results will not be accurate, so it will not be used. Even though you enable it, we don't use it. The next condition is the reinforcement area. If required reinforcement area is very large, the fast method may not accurate. So that's why you give a definition, maybe say 4%. If the required reinforcement area smaller than this, fast method will be used. Otherwise, still using the normal iterative method. If the fast method is used, you should know it is not an iterative method, so that's why it is faster. And the reinforcement calculated will be slightly conservative, maybe 1, 2, 3% higher than required. So, okay, I think that's all from me. I pass back to Chris.
Thanks, Thomas. In fact, we're going to go across to Rem Session, who's speaking from our Manchester office. I'm just passing control to Rem Session there. Over to you.
Thanks, Chris. Just trying to check if, okay, I think I'm audible. Let's see if I can. Try to move the slides. I think I can move the mouse, but not the slides. Is it right?
I'll click the first one.
Okay. Right.
And the next one.
Right, so we're going to be looking at the new diagnostic tools in GSA 8.7. So we have roughly three set of enhancements in this area. One is, the first one is the contouring of stubbiness. So this is to do with identifying elements that might contribute large stiffness values to stiffness matrix, which could make it ill condition. So we can now contour 1 over length of the element and area over length of the element. The idea is that if you have some really short beams or elements that have a large cross-section area and small length, then you can identify these very quickly. Right, so it worked now. I could move the slide, Chris. So that's what that contour would look like. So this model, we have 2 elements pointed out in red that have very small length. The next is contouring the loss of accuracy in force calculation. So the way this works is, if you imagine a simple bar with displacements U1 and U2 at its ends, then the force is AE by L times U2 minus U1. So we're looking at the difference of displacements of the 2 ends, and there can be a loss in accuracy in the force calculation if U2 and U1 have a large rigid body component, in which case, and if they are equal, in which case the difference could lead to cancellation in floating point arithmetic. And so the accuracy of result would depend on the relative displacements. So what that means is, if we separate out the rigid body displacements from the actual displacements at the 2 ends, then that gives us some idea of the amount of accuracy that's lost. So with this expression here, we separate out the rigid body displacement from the actual displacement, and what we're left with we call it distortional displacement, which is UD. And then if we take the ratio of U over UD, as we see here, and then take a look at that, that gives us the number of significant figures that's lost. And we can now contour this value on the model. So over here, the element in red signifies that we'll be losing quite a bit of accuracy in the calculation of this element. The third is model stability analysis. So this was a feature which was introduced in GSA 8.6. So if you saw one of these in conditioning messages when you carried out static or dynamic analysis, then you might have been interested in knowing what to do about it. So model stability analysis is a new analysis task that helps you detect where in the model you have errors that could cause ill conditioning. So these errors could lead to, as I say, a large condition number, which could further lead to numerical inaccuracies in your results. And so you would use a model stability analysis to find where these errors lie. In 8.6, we had the model stability analysis to detect what's called the low stiffness modes, which is errors that cause a lack of restraint or a lack of stiffness at a few degrees of freedom in your model. In 8.7, we introduced detection of both low and high stiffness modes. And we also added the contouring of results in the form of element virtual images, which makes it easier to spot the elements that are causing problems. So I'll come to what I mean by that in a moment. So if you have a model like this, which we, I mean, this model was particularly fine. We took it and tweaked it so that it had a few artificial errors. And then it started giving a large condition number warning that we saw a couple of slides back. So if that's the case, then we create a model stability analysis task from the analysis wizard. And then let's use a default of 20 modes each for those stiffness modes. And once the analysis finishes running, we could then contour the virtual energy result. And for this particular model, the errors we introduced were to do with lack of restraint on some of the beams, and that has resulted in highlighting those beams as ones having a large virtual energy in the low stiffness modes. So that's what the enhancements to the feature do. And there's quite a bit of information on what these low stiffness and high stiffness modes mean, and how to sort of make sense of these results and how to work out the number of modes to request and so on. And all that is now part of the manual, so it might be worth a read. Moving on to the new comment interface features. If you've used the GW command in the comment interface, you might have noticed how you'd have to assemble and disassemble strings in GWA syntax in order to get to the information you're interested in. So if even though it's sort of quite a powerful and versatile interface for getting and setting GSA model data, you still have to go through quite a bit of effort in the programming effort to manipulate these strings, and also have your code could run slower because of this string processing. So what we have in in GSA 8.7 is direct objects for nodes, elements, and sections. And what we mean by that is you have these structs which have been exported on the GSA comment interface, and they have these fields. So all you need to do is create objects of these structs, populate the fields, and feed them back into the into GSA using functions that accept arrays of these objects. And that way you can either retrieve or set nodes, elements, and sections in the GSA data structure quite quickly. So yeah, so that gives you better speed of access, and overall it results in cleaner code and code that's easier to use and understand. So to give you a comparison with GW command, if you have to set a beam element, this is what you would go through. So you would get hold of the beam keyword and then add the element reference and the property and the topology and so on, and then pass the string to the GSRevit command function. Instead, what you might have to do now is to create a topology array, then declare an object of the type GSA element, and then point it to the right element type, which is the bar, and then add the element reference and the topology array, and then insert it into a list of elements, which would then pass into the GSA. We call a GSA function to function to pass it into the GSA data structure. The other enhancement to the Comet interface are the assembly forces and displacements, which we discussed earlier. So we have the assembly feature in the interface now, and there is also a com function that allows retrieving those results using the API. Okay, that's all from me. Back to you, Chris. Thanks.
Thanks very much for your session. Just waiting to get control back again. There we go. Okay, so I'm going to whiz through a few miscellaneous items that have been introduced into GSA. You save with selected results only. Sometimes, if you've got a huge model, it's convenient to save models with just subsets of the results, so that it's easier to post-process. So, if you, in the Save As dialog, you can choose to save selected results only. You're then offered the option to define an element list and a case list. So, the resulting GWB file will include results for that list of elements and that list of cases. Import GWA options. There are quite a few enhancements to this feature. You can import results via GWA, combination cases, members, and design properties can be imported even when the results are present. And you can import user module data to be imported into an existing user module. Moving on to the more specific area of appending, there are now options to append axes, grid planes, polylines, material properties, stages, etc. And this is useful if you're working in a team of several people working on a particular model. Each person might be working on a different part of the model, and at some point you may want to merge those models together. So these enhancements to the append GWA help with that. Renumbering, we've added options to the manage data dialog to renumber lists of nodes, elements, and load cases. Auto option for load panels. When you define a load panel, you have to define a support type. The new support type is auto, in which case the actual support type used depends on the existence of non-dummy elements surrounding the load panel. Display list, drop list. Right, so the display list is that list of entities that define what you're looking at in a graphic view or output view. And the drop list is populated with all the currently saved lists, the current grid planes, and indeed the current assemblies. But working with a large model, it can be a bit confusing if that's all sort of intermingled. Now we've introduced the the idea of collapsing those categories. So here we're looking at collapsed lists but expanded grid planes. New element selection options. There's a new option, select by criteria. What we've currently got set there is that we can select all entities, all elements in this case, with length less than 0.01 of a meter, that are not vertical and that are colored hot pink. And we've said that we want to select the entities that meet all of those criteria. We could add to that list, so there's an add button there, and if we click that, we see what various criteria can be defined. Moving on to select by name, you can select all entities with a given name. That would be a simple match. Or you can use regular expressions if you're into that sort of thing. Regular expressions, you can get some help by clicking this button here, and it offers the various, or a subset of the functionality that's offered by regular expressions. So here we're looking to select all, looking at this currently defined regular expression, all entities that start with the letters roof, R-O-O-F, followed by a digit in the range 0 to 9. So select all of those roofs. Moving on to the new Omit from display cursor mode. If you select this new cursor mode here, then things you click on in the graphic view will be removed from the display. If you're coloring by type, then any entity that is that entity is removed from the display, and any other entity that has the same color defined for it is removed from the display. If your current color method is by property, then clicking on an element will remove all elements with that property, etc. And to help with this, we've got new accelerators that assist in defining the color method. So BP will set your color method to color by property. So here's a bit of a very busy graphic view, and if we want to look at some of those entities, removing the ones we're not interested in, then we click around on the ones that we don't want, and you can see here in the current element list how that's worked. Every time you've clicked on something, it's removed that entities with that property from the list. User module diagrams. If you've got user modules, then well, previously you could contour the user modules. Now you can produce diagrams for those as well. So those diagrams are of user module data. And in implementing that, we had to introduce the concept of values along elements at specified positions. Pin display. Okay. If you've defined your display list in terms of a grid plane, then typically, or very often, you will want to adjust the current grid plane to be that you've defined in the display list. So if you pin the display here with the pin display button, then selecting a grid plane in the display list automatically sets the current grid plane to the same grid plane. Contouring graded by value. That's in the contour settings, you can select this option, and when selected, then every value that is being displayed is assigned its own color. Now, obviously, this is only useful in certain data types. So we're about to display grid area loads. Well, we'll see how that works for grid area loads. So, in fact, in this particular model, we're looking at just 4 different values, and each one is assigned a different color. Not so useful for data types like well, bending moments, where you get millions of different values being displayed. So the contouring by graded by value is only offered for particular data types where it's beneficial. For example, grid loading and properties, etc. Condensed cases. Well, we're looking at grid area loads, and those loads are only available in some of the load cases that are offered in this, available in this model. And you can see from this, the size of this scroll bar, that there are many, many load cases in this model, and many of those don't refer to load cases in this grid plane. So clicking the condensed cases button reduces the list of load cases offered in that case list to just those that are relevant to what you're currently looking at. Right, interface with third-party software, new GsRevit functionality. We now use the Revit shared parameters for storing GSA member and element numbers, section names, section descriptions. And those are all used for coordination between Revit and GSA, where the more traditional coordination fails. So it's a backup to that coordination by SID and UID. We now introduce two-way coordination of element offsets and orientations, of curved members and of slanted columns. Right. Also, when importing and updating, we've introduced quite a few changes to, well, improvements to the mapping of sections and family symbols. So we can, there's an option to override the symbols from the GSA mappings database, override the ones that are currently in Revit. We can delete Revit entities where they're not present in the GSA model. We can define the family mapping via both by either the name or the description. The name will override the description. And we can also define the mappings, explicit mappings in the mappings database directly in the import dialog box. So the top half of this dialog box is a view onto the mappings database, and the lower table enables you to specify a mapping and then add that to the mappings table if you wish. And of course, we now have compatibility with Revit 2014. And finally, for those people who have access to the third-party option, Design Link Viz, there's a link to that from GSA. So this model has been exported from GSA to Design Link Viz, and there's an opportunity to visualize, to spin that around. So it's quite a nice visualization of the model. But perhaps more importantly is that there's an option to save that as a 3D PDF. So with a bit of luck, if I click this link, we will have a look at the 3D PDF that was created for this model. Click to activate. Take a moment to activate. Now's the time to be thinking of those questions, because coming up will be an opportunity to ask questions via the chat. Okay, there we are. There we are. We can spin the model around in this 3D PDF now. There we are. Over to you, Peter.
Thank you very much, Chris. Yes, indeed. So, as I said, if you've got any questions for the developers, do please type them into the questions box there. And I'm interested to see there is one already came in while you're presenting. This is on load panels. One for Steve, perhaps. It says, question from Will: do you still need to surround load panels in beam elements to make them work, or can we just put elements where the load panels are supported? Steve?
It's part of the algorithm for actually working out.
Sorry, I think you're muted.
Can you hear me?
I can hear you now. I think you're muted before.
Okay, I'll start again. Yes, you do still need to have elements around to define the edges. So you can't omit one edge and then have that one not loaded. So the way to accommodate that sort of thing is to put dummy elements around edges which you're not particularly interested in.
Okay. Couple of questions on steel design codes. First one is, can we now design explicit sections?
No, I don't think so. Yeah. We don't know the shape of explicit sections, so I don't think we can. Yeah.
Okay. Yep. And are we going to have Canadian steel codes at some point in the near future?
Not in the very near future, but it's always something we can consider.
Yep.
So by asking the question, that becomes something we consider.
Thank you much. I've got another question here. Maybe it's a more general one. Is asking about a webinar or tutorial on GSA Revit links, and yep, that is something we will see if we can include in the webinar program as it comes up over the year. There's a question about whether we can use rotational acceleration on models, and if not, can we add it to the list?
I'm not sure what that question means. Maybe that's one that we just need to pick up afterwards.
Yeah. Here also, if you want to email in and describe it, maybe describe it, discuss it more with us offline. I mean, you can already put in forces into the modal analysis, and maybe that's the trick. Okay, another question about, can we explain further the exploded grid plane loading corner method? For example, if a load panel is used but not exploded, which explosion method are we assume is being used? Steve, does that make sense?
There might be some. I think there might be some confusion between grid loading and load panels, 2D load panel elements. But with the grid plane loading, the method that's used is specified on the grid plane. So you can choose for any particular grid plane which expansion method you want to use. So you could have legacy for some, and you could have the plane approximation corner, for instance, for another. But that's completely different from the way that the load panel elements work, where the loading is determined by either the support condition, or in the case of the automatic one, it works out a support condition based on dummy elements around the edges.
Okay, thank you. We've got a question of when GSA 8.7 will be available.
Right. We're building what we hope will be the final beta today. There are more than 150 beta testers out there. And so we'll be providing that to them and anybody else who's interested in going on that beta list. The final release, well, depending on feedback from this final beta, the full release will be either next week or in 3 weeks' time. That sort of timescale.
Excellent. And which, of course, are all dependent on the beta testers not finding any problems. That's right. Which doesn't mean don't look for them, but okay. Tom's question for you: you mentioned that we can now use quad 4 and tri 3 shell elements in nonlinear analysis. Will we ever be able to have the parabolic, the quad 8s and tri 6s?
Yeah, of course, we are going to consider that, but for now, they are a bit of difficulty to me, maybe not to other experts, but we will look into it in the future.
Okay, thank you. All right. That appears to be the end of the questions, unless someone sneaks one in very quickly. Thank you all for attending. Just to let you know that... David, you snuck one in. For those of us who haven't used the Ritz analysis methods previously, could you explain this from a more entry-level or beginner perspective? Steve, what is difference?
30 seconds.
What's the difference? What's the difference between Ritz and Modal analysis? In layman's terms.
Right, I don't think it can be explained in 30 seconds. I believe there's going to be a webinar on this sometime later in the year. Is that right, Peter?
I think
but
so.
The basic idea is that, yeah, basic idea is that you use a set of load vectors to get you started, and then you use that to project onto a smaller system. So it depends on setting up load vectors, and the ones we use are just a gravity load vector in the X, Y, and Z directions. Then what it does is an approximate model analysis, and there are certain sort of conditions that are guaranteed by it. So the advantage of the Ritz analysis is that it's better able to pick up things like vertical modes where the dominant vibration is horizontal, those kind of things. But it's a bit, we need a little bit more time to explain it properly, which we probably haven't got just now.
Fair enough. But I think, well, one of the basic things, it's okay for seismic analysis, but not for, say, floor vibration. That's the thing, because it's more approximate.
Yeah.
Okay, and another question stuck in, I think this one for Thomas. The 2D shells in non-linear analysis, can we use non-linear materials with those? Say cracked concrete, yielding and so on.
Yeah, the answer for now is no. So the shell element can only use elastic material for now. For the future, depends on, yeah, we are looking into it definitely.
Excellent, excellent. Okay. Well, that looks like the end of the questions. So just leave me to say thank you all for attending, and thank you guys for your excellent presentation. We will put I've been recording this webinar, and we will be putting the video online in the next day or so. We'll also put the PowerPoint slides online as well for you to look back over. And if you've got any further comments and so on, do drop us a line, and thank you all for attending. Goodbye.